Emostel.
Hello, hi MIVA. This is the second class that we're going to be having on the first classroom session on Physics 101. Okay, now still on vectors, but this time around we want to go a little bit deeper to cover the parts that we couldn't cover in the previous video. Bear with me. Now, in the previous video, we have the following summary. Provided that we have these polar coordinates, all right? Polar because it deals with angles and then represented on the graph, okay? All right, and then this is a two-dimensional graph. Vectors can also be represented in three-dimensional graphs, and I'm coming right to that later on, okay? But now we have a two-dimensional graph that contains the vector R, okay? The length of that vector represents its magnitude, which we can represent symbolically as the magnitude of R. That is the size of the vector, the value of the vector when we measure it. No, we are not specifically talking about a particular vector. Now, I told you vector can be force, can be acceleration, can be displacement, can be anything that has magnitude and direction. But this is just a general representation of any vector, whatever the case may be. So we have represented the vector on the polar, on the x and y axis. Okay, so and we have also verified the polar coordinates, which is the rx, the ry, which is the projection of the vector on the x-axis and the y-axis respectively, and we have been able to have all these deductions from it. Okay, then what next? This conclusion here gives us the direction of the vector r. It gives us the direction of the vector r. Then how then can we find the magnitude of that vector, like to calculate it, to obtain it? Okay, let's say we are not using the length of the line. The length of the line actually represents the magnitude of the vector, but now we want to calculate it. So we want to derive a formula that can be used to calculate that magnitude. That is what we want to do right now. So we have been able to get a formula to calculate the direction. Remember again, a vector quantity is a quantity that has both magnitude and direction. We have been able to derive a way to find the direction by calculation. So as long as we know the value of the vector along the x-axis and we know the value of the vector along the y-axis, we can fix it in here, calculate it. When we divide and we get the results, we look for the arctan of that result, and then that gives us the direction. We're still going to have empirical examples later on. Okay, that is the mathematical, the numerical example and all that. So now we have gotten the formula for the direction. We want to find the formula for the magnitude. Let's bring back this triangle here. Now, this is the hypotenuse, okay? This is the components of the vector along the x-axis and the component of the vector r along the y-axis. So as it is here like this, is the same value here like this, from here to here. Okay, so represent it like that. Now, trigonometry makes us to understand from Pythagoras' theorem that the square of the hypotenuse, this is the magnitude of the vector, the size of the vector, okay? All right, so trigonometric ratio makes us to understand. Sometimes we will not bother putting this bar beside it. They just write only R, it's okay. It's okay. The vector of R is represented by R and an arrow. The magnitude of R is represented either by putting a bar or just by simply saying R. So if R is what is there, no problem, you are still cool. As a matter of fact, I even prefer it that way. It makes this look more presentable. So at the end of the day, so you have this as R, blah, blah, blah. Pythagoras theorem says, remember the Pythagoras theorem now, which says if the hypotenuse is A, and then this is B and this is C, however, the Pythagoras theorem says the square of the hypotenuse is equal to the sum of the squares of the two other sides, which simply means that this is the hypotenuse, the line that is facing the angle. Okay, so which means R squared is equal to Ry, or let me just make it in order, it's the same thing of Rx squared plus Ry squared. Right? I'm here right now, vector addition in polar coordinates. That's what I am now. Okay? Now we have R squared is equal to what? Rx squared plus Ry squared. And then when you have it that way, Rx is the component of the vector R on the x-axis, Ry the component of the vector R along the y-axis, and then this is R here. So the square of the hypotenuse is equal to the square of the sum of the squares of the two other sides. That is what we call the Pythagoras theorem. Now, so which means that the magnitude of the vector is going to be equal to the square root, because this square, by the time it goes to the other side, it becomes a square root over Rx squared and Ry squared. All right, again, that, and that is that, as for that. Okay, let's just quickly have, so this one is the magnitude of the vector R. The magnitude of the vector R. This is the formula for the direction of vector R, and this is the formula for the magnitude of vector R when we represent it on in form of the polar coordinates. Do you understand? Good. So now bringing it back to, let's just do a calculation. Let's see. Let's say Rx is equal to 3. Let's say Rx is equal to 3, and then it can be 3 meter per second, 3 meter per second squared, whatever vector it is, whether it is force or whatever. I just only give you the magnitude. Okay, the magnitude is 3, and then let's say Ry is 4. Okay, then find the magnitude of vector R and the direction of its vector R. Find the magnitude of vector R and its direction. Magnitude of vector R is less than ordinary R or R with a bar around it. Okay, or the direction of the vector R. Okay, if you want to do that, all you just need to do to find the magnitude, just say that what R is equal to the square root of 3 squared plus 4 squared, according to this formula here. Okay, and then you have it as the square of 3 squared means 3 times 3, right? And that's 9. 4 plus 2 means 4 times 4, and that is 16. And then we have square root of 9 plus 16 is 25. The square root of 25 is 5. So it means the magnitude of this vector R is equal to what? 5. I mean 5 Newton, 5 whatever. Okay, so that is the magnitude of vector R. This is the unit of force. The meter per second unit of displacement, and so on and so forth. The meter per second is the unit of acceleration, and it goes on like that. But because we are not specifying the form of vector here, just only write the value, which is what? 5, the magnitude, and that's all. So then if the question says find the direction, okay, this is magnitude, we just found the magnitude now. Then to find the direction is always given in form of angles. So which means the direction is like this, acting of the Ry given as 4, divided by Rx given as 3. So when we calculate 4 divided by 3, and I'm going to load my calculator here to find the angle theta. Okay, excuse me for that. Alright, so to find the angle theta, what to do here, first say 4 divided by 3, right? Okay, 4 divided by 3, we have arctan 4 divided by 3, 1.3333, right? So arctan of 1.333 is different from tan of 1.33. Arctan is, we are looking for the angle which tangents give us 1.333. Okay, so what is that going to be? To test arctan, if you are using the castle calculator, press hit tab or whatever. Okay, so I trust you know how to go about that. And so we go to inverse of tan. Inverse tan of 1.3333, and then close the bracket. And that gives us 53. Okay, like let's just say 53.1 degrees approximately. So, which means that the angle between the vector, which means the direction of this vector is what? Is 53.1 degrees. So, if you want to represent this vector generally now in form of magnitude and direction, you just say vector r, in form of magnitude and direction, vector r, the magnitude of that vector is what? Is 5, maybe 5 Newton, if it is in force, or 5 whatever, okay, comma, the angle is 53.1 degrees. So this is represented vector r by indicating its magnitude and its direction. That is just how it goes. Okay, so this is a polar representation, a way of representing the magnitude and the direction of the vector, of a particular vector, in form of its polar coordinates. Okay, in its polar form, the magnitude here, and then the direction in degrees. Okay, derived from this polar whatever, and then we got it. All right, good. So quickly, we move on to the next one. I want to explain the one of Cartesian coordinates. Okay. All right. To be honest, we are going to still represent the vector along the x-axis, the y-axis, okay, and we have this. This time around, we are not necessarily talking about angles, okay, but importantly referring to the component of the vector along the y-axis and the x-axis. Now, let's take for instance, this is like 1, 2, 3, or whatever value it is. Okay, whatever unit you have decided to choose. 5, 6. All right, and then let's say this is 3, 2, 4, 6. We have 8 or something like that. Let's just assume. And then we have 8 in this way. Okay? And then you choose this young man here. Let me play my phone. I just want to see I don't want this now, whatever. Okay? So And then we bring this one here like this, and we trace it to the y-axis. Okay, but we're still talking about this vector r. Okay, if you do this, you can say vector r. This is in form of Cartesian coordinates now. Cartesian coordinates. Okay, you can say vector r. The Cartesian, what we really refer to as Cartesian, is representing something in the form of x, y. X, y. That is the value of that particular vector along the x-axis and the value of the same vector along the y-axis. Okay, so this is the Cartesian coordinates. Okay, all right. So that is what we have here as x and y. So which means if I want to represent this vector r, I can say vector r has the y-axis. It has 4 units because we count 1, 2, 3, 4. It's correct. Vector r, okay, has a component of 4 units along the x-axis, and so we have 4, comma, and it has a component of 8 units along the y-axis. So we have what? 8. So by representing the vector in this manner, r into bracket 4, comma 8, we have been able to represent this vector r in Cartesian coordinates. We are saying that r is what? So whereas this first value always represents the x value, and the second value always stands for the y value. You get that? So we have just carried out the Cartesian coordinate representation of this. But alternatively, there is a way you can also represent this same vector if you do not want to do it this way. But you should understand that the unit vector across okay, across the x-axis is represented by I. The unit vector across the y-axis is represented by letter J. If we have a 3-dimensional plane, that is 3 axes, x, y, and z, take value to the unit axis across the z-axis and the unit vector across the z-axis is what? It's represented as k. I'm going to show you an example of 3-dimensional plane, but let's still move on. Okay, if you have it this way, then you can easily represent this same vector. So which means that if you don't want to write it this way, okay, instead of saying x and y like we have it here, you can say, oh, this vector r is made up of 4 units. The unit vector across x-axis is I, right? 4 units across the x-axis, 8 units across the y-axis. So you can easily say r is equal to 4i, which is what? Y plus 8j. You can say r, vector r is equal to 4i plus 8j. Alright, vector r is equal to 4i plus 8j. If you don't represent it in this way, you can also represent it in this way. They still pass the same message, they still speak the same language, they still say the same things. Okay? And that is the way it goes. Alright? So it is still exactly the same thing that we are talking about here. Then we could still do the same like this. So which means we make the vector r by counting 4 units across the x-axis and 8 units across the y-axis. Okay? Take note of this before I take it off. That the unit vector across, I'm still going to tell you what unit vectors are. Okay? But before I get there, just understand that the unit vector across the x-axis is represented by I, the unit vector for y-axis is represented by z, and then how did this even come to be? Let me just give you a sneak peek over it for now. The y-axis itself is a vector. X-axis itself is also a vector. And then, why did I say it's a vector? It has a magnitude, which means the values across the x-axis can be measured. It also has a direction, which is this, okay? There's no how you draw a graph and then you represent the axis of that graph, but you able to indicate the direction. So at the end of every axis, you always put an arrow. So this arrow that is here tells you the direction of the vector in each axis. So which means it is facing here. So just as we have the positive x, we also have the negative x as well. So which means every value here is -1, like this, -2, -3, and so on and so forth. We also have the negative y, like this will be -2, -4, and so on and so forth. So as the direction goes down, okay, it becomes negative then, which is the opposite vector to the positive side. Do you understand? So, like I said, if you really want to know more, if you want to dig deeper into vector, vector is very sweet, very interesting to learn. But if you want to get to know more about this, just follow that video. That's the series of videos we did particularly on the vectors. But this one, we're talking about physics. We just want to have a sneak peek of the vectors, just to explain some basic things. We are not going too deep. But for curiosity, you can feed it by watching the videos on vectors. Okay, so now back to this. Each of the axes have their vectors themselves. Okay, but the value on each step that you take on the axis is what we call the units. All right, I take one step from here to here. That is the unit vector 1 across the x-axis. Okay, I take another one step again because a unit vector is a vector whose magnitude is equal to 1. The magnitude of the unit vector is 1. So I take 1 unit, and then I took this vector covers up to 4 units across the x-axis. That is why we have 4i. The magnitude is 4. Okay, so the direction is this. So we have 4 units across the x-axis and then 8 units across the y-axis. So which means if you have this to 1, 2, 3, 4, 5, 6, 7, 8, we count 8 steps. Let's the axis can have any value to represent some key parts. So which means that if this one is 2, definitely 1 will be somewhere in the middle, 3 will be somewhere in the middle, so on and so forth. Okay, so but the key parts on the y-axis are represented in 2 units each, while the key parts on the x-axis represent 1 unit each. Is no problem, but it can be the unit vector is just a vector whose magnitude is 1. So because we count the magnitude 4 times, 4 units, that is the reason why we have 4i. And then for each unit across the x-axis, that is the reason why we have 8j, because the unit vector of y-axis is represented by j. Do you understand? And then if we have a 3-dimensional plane, the unit vector is represented in that case as k. You understand? So now, back to this. In case I have something like maybe I do a vector represented along these parts, a vector along this part, and this is minus x, negative x. This is the positive x-axis, the positive y-axis, the negative y-axis, and then placing this vector into this place. Let's say we have 1, 2, 3, 4, 5. That's negative 6, -7. So we have 1, 2, 3, blah blah blah. And then here, let's say we have 5, 10, 15, and then here -5, -10. Let's be anything, okay? So you can choose your units across each axis. And so let's say when we trace this one to the y-axis, we got 10. We represent this vector as what? As vector r is equal to what? How many I represent the unit vector across the x-axis. So it falls on the fifth one. So we have minus 5I plus what? How many j? 10j. Okay? Plus 10j. Got it? So let's say I have another vector represented like this. And you trace it to this one now, minus 6. You trace it to the other minus 15. Okay? You want to represent this one. Let's say this is vector R. Vector S. You see vector S here in this case is what? Minus 6I. Minus 6I. That's negative 6 units across the negative side. That's why we have minus 6I. That's the side of the x-axis. Then how many units across the positive side of the x-axis? Any units? No. But for the y-axis, we have this minus 15. So we have plus minus 15j. And because in mathematics, minus is minus. Okay, when two different signs multiply, the result is always negative. But when two same signs multiply, the result is always positive. So we just make which is minus and minus is plus, plus is minus plus. But people when they are different signs, the result is negative. So now plus is minus is minus. And so you end up saying minus 15j. So this one is represented as what? Minus 6I minus 15j. You got that? Alright. So now, if you have something like this, for instance, and you call it vector P. If you trace it here, you trace it here, you have vector P is equal to the positive side, okay, x does 3I plus, if you trace it to this place, you have what? Minus 15j. This time minus 15j, and so on and so forth. So that's just how to represent vector in this form. Now you'll be talking about this plus that is here. I'm still coming back to that. Okay, if we now want to talk about, we want to find the magnitude of the vectors. Okay, now, okay, let me quickly explain the reason for the plus. The plus that we are seeing here, okay, it stands for the resultant vector. The resultant vector of R is the overall effect of this vector R on each axis. Okay, vector R, for instance, like this, it has some impact on the x-axis, some impact on the y-axis, which is a component, and that's what we have represented here. So the overall impact of vector I is represented by the addition of its impact on the x-axis and the impact on what? On the y-axis. So when you add two vectors together, you get what we call the resultant vector. So that is where the plus that you have been seeing here comes. Which means the overall vector, the overall effect of vector R is equal to what? The effect on the vector R on the x-axis plus the effect of the vector R on the y-axis. Okay, so that's the essence of the plus that you are seeing here. This minus is still means plus, but because there is a plus existing and there is minus 15j, all right? Now, the plus is still always there, but this time when the plus was taken over, so they say plus times minus is minus, that's why you have minus 6I minus 15j. But ideally, it is given as minus 6I plus minus 15j, which means the negative 6, because this I and this j, they are vectors themselves, right? I told you that the unit vector is the vector whose magnitude is 1, and every vector is a product of its magnitude multiplied by its unit vector. So the magnitude of this one is 6 because we counted 6 units. The size of the vector across the x-axis here is 6, and then we count, that is the magnitude. The I is what? The unit vector. All right? So I mean, going too deep into this, I can start confusing you. So let's just keep it the way it is. But if you want to know more, you can always contact me. I will explain. All right. I'm trying to save the time for the video. Okay. What is that I've explained? I've explained the meaning of resultant vector, which is the overall effect of the component of the vectors, okay? And then, okay, now good. It remains how to calculate the magnitude of vector when it comes in this manner. Calculating the magnitude of the vector when it comes in this manner. Let's go. So, but before, okay, yeah, let me just quickly explain that. If vector R is equal to 4i plus 8j, for instance, okay, which means generally vector R is equal to xi plus yj, all right? If vector R is equal to xi plus yj, the magnitude of vector R, you see that I did not put the arrow on it, which means I'm talking about the magnitude. Just like we did earlier, is equal to the square root of what? X squared plus y squared. This is the general formula for magnitude of vector given in this form. You know the magnitude of vector given in the other form too. Okay, the Rx and the Ry and all that. Okay, so in this form now we have I and J. Okay, if the vector is given in this form, okay, to find the magnitude is still the same way you found the magnitude earlier when it was given in form of its polar coordinates. Okay, now as it is given in this Cartesian coordinates form in this place, whether it is written this way or written this way, if you want to find the magnitude, whether it is written this way or written this way, if you want to find the magnitude, is the same thing. Just take the x components and the y components, square them, and you are good to go. Square them and then add the square and find the square root and you are good to go. So therefore, the magnitude of vector R is going to be equal to the square root of 4 squared plus 8 squared. You understand? And then, which means the magnitude of vector R is going to be equal to 4 times 4 is 16, 8 times 8 is 64. Then the magnitude of vector R is the square root of 6 4, that's 10, 0, 1, 8, the square root of 80. So you find this value of the square root of 80, and that is the answer for the magnitude of that vector R, the size of the vector R. So whatever answer you get, maybe the vector you're trying to represent is in Newton, so Newton, so this and that. You get? So if, for instance, we have an example, you can pause the video, write this down to follow up, but I'm erasing it now. Okay? Let's assume we have a vector given this way, R, okay, and it's just the same. Okay, let me give you the words. If force of 30 Newton is applied on a ball, by pulling in a direction and another force of 40 Newton applied in another direction, I just quickly crafted this question just to prove a point, okay? So it's not really, you can just play with other questions with the knowledge that you gain and all that. So another direction with a force of 40 Newton, okay, apply the other direction, sorry. Find the resultant force on the ball. Okay? All right. So this is not really a standard question, but yeah, it's still good. All right. So a force of 30 Newton is applied on the ball by pulling in a direction, and another force of 40 Newton applied in another direction. Okay. Find the resultant force on the ball. Let's say the ball is pulled through this direction, and also pulled, this is the ball, and also pulled through this direction. pardon the question, right? I will have probably indicated the direction to make the question more standard and agreeable. Okay, I can say it was pulled in the north direction and then pulled in the eastern direction with the force of this. Okay, and then so let's say a 30 Newton force is applied like this, a 40 Newton force is applied this way. Definitely the ball will neither go this way nor this way. It will go somewhere across the two of them, the middle of two of them. Okay, so the ball will go like this. If you pull it simultaneously through these two directions with this amount of forces, okay, 40 Newton, you want to calculate the resultant effect of these two forces on the ball, all right? So we know that it is going to be like this, according to the triangle, the parallelogram law of vectors. Okay, the parallelogram law of vectors says if two vectors are vectors A and B, are applied in magnitude and direction on, it says the resultant vector is represented by the what's it called, the diagonal line that passes through the center of the parallelogram. Okay, so this is the diagonal of it, the diagonal line through the parallelogram. So because if I complete this thing like this, I complete this like this, then I formed a parallelogram. Okay, like this. The diagonal line that passes through their meeting points is it. Okay, so this is the force of 30 Newton, the force of 40 Newton, and this is the resultant force. The resultant force is represented by the diagonal line that passes through the point of impact. Okay, the line. Okay, this is the parallelogram law of vectors. We also have the triangle law of vector too, which says that if two vectors are represented in magnitude and direction on two adjacent sides of a triangle, it says the third side, okay, represents the resultant vector is represented on the third side of the triangle. Okay, that's the triangle of vectors, but it's not covered in this scope, so I'm just trying to stick to it. And it is from the parallelogram of vector and triangle laws of vector that the resultant vector, the addition of vector is formed from. Okay, so now we have it this way, like this. So what the question is, what the law is just trying to tell us is that the overall effect of R, okay, the overall effect of the two forces of this ball is given as the addition of the two other forces, which is 30 Newton plus 40 Newton. That's where the addition of vector comes from. But the addition we are talking about is not a direct addition. If you want to find the magnitude of this vector, you will say, yes, theoretically it is written this way. That is, the overall effect of this vector R is equal to the sum of the effects of the two other vectors, 30 and 40. That is the law. But if you want to do it in calculation, by calculation, the magnitude, I'm not talking about the vector itself, the magnitude of the vector. We have already known the magnitude of this vector as 30 Newton here. We have known the magnitude of the vector in this direction of the second one as what? As 40 Newton. Okay? Then the overall magnitude of the vector is going to be represented as what? As in R is equal to the sum of the squares of the two vectors. So we have 30 Newton squared or 30 squared plus 40 squared. And then that's going to be equal to the square root of 900 plus 1600. And then that's going to be equal to the square root of 2500. And then the answer is what? 50 Newton. So which means that the magnitude of vector R is what? 50 Newton by this calculation. Okay? And so which means the vectorial addition is different from algebraic addition. By algebraic addition, we say 30 plus 40, which will be 70. But vectorial addition, 30 plus 40 is what? 50. By algebraic addition, normal algebra, 30 plus 40 will give you what? 70. But by vectorial addition, 30 plus 40 gives you what? 50. And this is how it happened. Okay? And so, by so doing, we have come to the end of this video. I've been able to refer to this side, and we've gotten there. We've also talked about the vector addition in Cartesian coordinates, which we just finished discussing, and then how Cartesian coordinate vectors can be represented. And then the last thing we're going to be talking about is the unit vector. I'll see you in the next video for that. Bye.